Hi, this is Someshwar.
Hi, this is Bhavya Raj.
And my name is Bharat.
And we're gonna explain the Capstone project's working in this video.
Quantum Telery, polarizer-based synchronous optical communication system. The optical communication arena has perceived a surge in its usage and promising future recently. In this tempest for excellence, getting a versatile and efficient mode of optical transmission is inevitable. Following this, our idea contributes a vital stride forward by proposing a new modulation scheme based on the polarizer's intricate working. Due to their complicated quantum results of the three polarizer paradox, polarizers are still unique in their practical usage in different fields. Our new scheme uses the source optical intensity and wavelength as the varying parameter for message data encoding, which can also be termed the merger of the amplitude modulation and chromatic shifting, accomplished by polarizer's specific orientation and externally modulating it. The rotation of the polarizers into known orientation yields a predictable intensity backed by physics equations. The output into quantized intensity levels serves our purpose of communication, where we try to translate the binary values into optical intensity levels essential for communication. Our study includes the requirements and performance of different components essential for transmission and reception. Moreover, the idea is compatible with the conventional optical sources in the visible region, such as laser or LED. Implementing further advancements in the field of encoding techniques like Huffman coding can increase the efficiency of transmission significantly. The graphical user interface backs the modulation scheme for user friendliness, along with numerous transmission options it provides. We further proceed to detailed applicability of the photoelectric effect and design an optical intensity receiver using LDR on the receiver side, enabling proper decoding of the transmitted message. The objectives of the project are to introduce the idea of external modulation techniques, to comply with the proposition of one-to-many mapped communication system, to present the possibility of attaining different DTRs in simultaneous channels with a common source, to propose a fast yet power-wise efficient modulation scheme, to offer an adaptive communicating scheme, to continue with the virtually non-existent EMI feature of optical communication. The intensity of the source is controlled entirely by the polarizers, with rotation into specific orientations that is even verified by experimental procedures. The polarizers are also found to suppress specific wavelengths of light and hence making the incident light appear redder or bluer based on the orientation.
For efficiency, we employ the use of Huffman coding, which is a distinct type of variable length encoding algorithm that results in an optimal mode and the highest efficiency of transmission. The coding technique is fed with prior knowledge of alphabets occurrence in English language as symbols for assigning the particular code to each of them. The special case of our codes clinched a 99.3% of transmission efficiency. Similarly incorporated the RSA algorithm to satisfy the requirement of security in the communication channel. Rivest, Shamir, and Adelman developed this algorithm using the public and private key encryption technique. It is one of the most convenient and secure ways of encryption.
For intensity modulated light reception, characterized LDRs can be used. We exploit the linear operation range for the LDR to convert the light intensities to corresponding binary bits. We follow the same decoding scheme with LDR as shown in the table. Detecting the chromatic suppression was quite a challenging task since there was no such sensor at our hand. Instead, we went on to design such a sensor theoretically which can serve the purpose. You might remember the property of metals emitting electrons when subjected to light to frequency greater than its threshold frequency. The well-known photoelectric effect has a direct mathematical relationship of the frequency of light and the kinetic energy with which the electron is emitted. Simplifying it enough, the output current will give us enough information to decode if the light is of red spectra or blue.
Let us show you how the GUI helps in the transmission and reception process. The setup mode can be used to control the basic source characteristics and functions. For the current transmission process, we make the source intensity 100% and select the bit mode and advanced mode in operations. At the receiver end, it is imperative to model the channel characteristics by sampling the max intensity and minimum intensity. We then type the message to be transmitted. The backend, comprising of all the functional blocks, converts the message into corresponding binary sequence and then symbols. Although the transmission process would be completely automated, we had to do the rotation manually because of unavailability of components in this lockdown. After receiving all symbols, the backend converts the binary sequence to the corresponding decoded values, rendering the successful transmission of message. Just have a look at another mode of operation in action. The real-time working for the same transmission is shown in this video. The lighting system acts as the inferential system, guiding when the polarizer system is in correct orientation to transmit. We move the polarizer to get the blue light and green when the receiver successfully receives it. We lastly show the advanced version of transmission, where each symbol corresponds to 3 bits, 2 intensity bits and 1 chroma bit. We have shown both the real-time working and the GUI control this time, so that it will be evident how it works with a real user.
Output spectrum gives a significant insight into the overall spectrum that gets transmitted through the channel. However, we also notice that the other spectrums except blue and red prove to be useless and render power wastage in our case. Therefore, after observing the spectrum of light, we sense that if we use just red and blue light, we can mitigate the wastage and save power. Moreover, in our idea, we have used the photoelectric effect to procure the results that involve just the mode of chromatic suppression. Instead, we may use the phenomenon to observe for any of the modes given. The domain of the photoelectric effects does not restrict to the boundaries of chromatic suppression, and it can be implemented for the combined mode.